Hello, everyone, and welcome. My name is Reductive. I'm a senior principal at Geosyntech Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. This webinar will consist of a brief overview of both programs, followed by the technical portion of the webinar on innovative techniques to remediate 1,4-dioxane in the presence of other chlorinated solvents. We'll kick off with Dr. Bruce Rittman from Arizona State University, who will discuss the use of a linked hydrogen-based membrane palladium film reactor in sequence with an oxygen-based membrane biofilm reactor to treat groundwater contaminated with 1,4-dioxane mixed with TCA and TCE. Bruce's presentation will be followed by a Q&A session. Then Dr. Jens Blotefogel from Colorado State University will discuss his SERDP-funded research on coupling electrochemical water treatment with biological degradation to treat 1,4-dioxane in mixed plumes. Jens's presentation will also be followed by a Q&A session, and we will conclude the webinar with a longer Q&A session featuring both of today's speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you are unable to view the slide or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, just call into the conference line shown here. You may also submit a comment using the chat box, but please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. In case of continued difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Note that we will be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. So that's another way you can access today's webinar. The broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. We encourage you to submit them well in advance of the Q&A questions. And when you do submit them, please make sure to add your organization name at the end of your question so that we can properly identify you. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with SERDP and ESTCP since 2001, and prior to that, she was a research leader at the Battelle Memorial Institute, where she conducted scientific research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Thank you, Rula, and thank you to everyone who joined our webinar today. What I'd like to do today is give you a very brief introduction to who we are in terms of SERDP and ESTCP before I turn it over to our first speaker today. So we are companion programs in the Department of Defense. We work on environmental technology. The first program is the Strategic Environmental Research and Development Program, and this is our science and technology program. It is a partnership between the DoD, the Department of Energy, and the EPA. And we're really looking to take research, fundamental research, to impact real-world environmental management. Our companion program is the Environmental Security Technologies program, and this is our demonstration validation program. And so often what happens is the knowledge or the technologies that are developed under SERDP or under other research programs, not just ours, as they mature and are proven effective, they move into ESTCP, where we can demonstrate and validate these technologies in the field. And it's very important, this program has been very important to transition this technology out of the lab and to the end users. We do a lot with establishing the cost and performance of the different technologies so that you have this information when you want to go full scale. We have a few drivers that impact the research and demonstrations that we fund. The first is sustaining the training ranges, facilities, and operations on our installations. This covers a wide variety of topics from maritime sustainability to forward operating bases, dealing with unexploded ordnance, munitions constituents, etc. Very broad impact. We also look at reducing current and future liability. This can be in traditional pollution prevention to control these life cycle costs, and this is by eliminating or mitigating hazardous components or processes on our installations in the manufacturing, maintenance, and operations. And then we're also dealing with contamination from past practices. This could be contamination that's impacted our groundwater, soil, sediments, as well as dealing with emerging contaminants, those chemicals that we were not aware of until recently. And the talks you'll hear today are addressing one of these emerging contaminants. As I mentioned earlier, the technology transition is very important to us. We do this in a number of different ways. Everything is available on the SERDP and ESTCP website, but you can find there videos, in-person training, guidance. We have an EnviroWiki, a play on a Wikipedia. And then finally, we have these webinars. These webinars come out every 2 weeks or so, and it is on a variety of different topics. Everything we fund comes into these webinar series. Shown here is a list of some of the upcoming webinars, and you can see we have several that are coming up talking about PFAS, AFFF, we have munitions response, many different topic areas coming up. If you go to our website shown here, you can get more information about each of these webinars as well as register for them. And before I end, I would also like to mention that our SERDP and ESTCP symposium is coming up at the end of this year. This is a great opportunity to really see the breadth of everything that's funded under SERDP and ESTCP. All active investigators present at least a poster, with some investigators also giving platform presentations. We also have a call for abstracts out that is open to anyone, not just people we fund, and I encourage you to take a look at that. Those abstracts are due July 15th. At this point, I'd like to turn it back to you, Rula, though, to introduce our first speaker.
Thank you so much, Andrea. It is my absolute pleasure to introduce our first speaker, Dr. Bruce Rittman, who is Regents Professor of Environmental Engineering and Director of the Biodesign Sweetie Center for Environmental Biotechnology at Arizona State University. Bruce's research focuses on the science and engineering needed to manage microbial communities to provide services to society. He is a member of the National Academy of Engineering and a distinguished member of the American Society of Civil Engineers. He is also a fellow of the American Association for the Advancement of Science, the Water Environment Federation, the International Water Association, the Association of Environmental Engineering and Science Professors, and the National Academy of Inventors. Most notably, Bruce is the co-winner of the highly prestigious 2018 Stockholm Water Prize. He has published over 730 journal articles, books, and book chapters, and he has 17 patents. Bruce, we're delighted to have you. Please proceed.
Great. Thank you very much, Rula and Andrea. I'm very happy to be with everyone today to talk about this topic of the synergistic reductive dechlorination of 1,1,1-trichloroethane and trichloroethane and aerobic biodegradation of 1,4-dioxane. This is a SERDP sponsored project, and we've got some very interesting results. So here's the outline, and we'll start with the problem, and we'll finish with the benefits, and all the really important stuff is in between. So let's get going with the problem. This is not unknown to anybody on this webinar. We have co-contamination of 1,4-dioxane plus the solvents TCA and TCE because 1,4-dioxane is a widely used stabilizer. The TCA and TCE are regulated pollutants by the US EPA, and the states have regulations, more coming all the time for 1,4-dioxane. So these are real problems, and they usually occur together. So here is a view of the overarching technical objective of our project. And so you can see the little graphic at the top. Coming in on the left into our system is the co-contamination of TCE and TCA and dioxane. In a first stage, a reductive hydrogen-based stage, we are going to reduce the TCE and TCA to ethane. The dioxane will pass through that first stage. And then in the second stage, we will have an aerobic biodegradation of the dioxane and the ethane, and it'll be a co-metabolic process, and the ethane is essential for driving the biodegradation of the dioxane. And these two then are run in series, so that's why we call it a synergistic process. So as you'll see as I go along that the foundation for both stages of this are what we call membrane film reactors. And in membrane film reactors, we use gas transfer membranes to directly deliver a gaseous reactant to the catalyst. And that catalyst is on the surface of this gas transfer membrane. So this all began about 20 years ago when we started working on the hydrogen-based membrane biofilm reactor, or MBfR. At the time, nitrate was a big problem for treatment, and then perchlorate burst onto the scene, and the hydrogen-based MBfR works really, really well to remove nitrate and perchlorate. We've subsequently used it for a whole wide range of other oxidized contaminants, including selenite, chromate, and the chlorinated solvents themselves. So here is what it looks like. This is sort of the technical foundation piece. So in this diagram on the right, you can see a cutaway diagram of a hollow fiber membrane. This is a non-porous, bubbleless gas transfer membrane. And in commercial practice, they're usually made out of polypropylene. Hydrogen gas is delivered to the interior or the lumen of the membrane. It diffuses through the wall and comes to the outside where there's a biofilm that is growing in contact with water. The biofilm is oxidizing the hydrogen that's coming from inside out, and it's using those electrons to reduce things like nitrate and perchlorate going outside in. So the biofilm is the meeting ground for the hydrogen and the oxidized contaminants. So here are some pictures of some laboratory scale systems that we use all the time. We just build these on the head of a peristaltic pump, and that pump recycles the water through the system to keep it well mixed. The pictures on the right are particularly illustrative because you see two MBfR systems. The one on the right is a new one and was recently fabricated when we took the picture, but the one on the left, you can see it's brown. And this is the biofilm. So the biofilm has naturally grown in this one, and you can see it with your eye. Now, that's a bench scale, but the MBfR is a commercialized technology, and it's commercialized by the company APT Water, one of our partners in this project. And you can see two pictures of full-scale systems here that they have installed for nitrate removal from groundwater. So it's commercial technology. You can buy it for things like nitrate reduction. Okay, so now let's get back to the specifics of TCA, TCE, and dioxane. First, we'll turn our attention to TCE and TCA, chlorinated solvents. So what we want to do is reductively dechlorinate them. And so here on the right side of the graphic, you can see the two streams for TCE and then TCA. And step by step, hydrogen is oxidized, and one H goes into the molecule to replace a chlorine substituent. The chloride comes off, and we step by step reductively dechlorinate this. Now, what's really important here on this is that at the very bottom, you'll see circled in blue ethane. So our goal here is to get absolute complete reduction all the way to ethane, whether we're starting with TCA, which is already an ethane, or we're starting with TCE, which is an ethene. So we want to be able to do that last step for ethene, the TCE. Okay, so that's sort of the scientific foundation for the first step, reductive dechlorination. Now here's the scientific foundation for the second step, the aerobic biodegradation of 1,4-dioxane. This has been fairly well studied, so there's no mysteries here on this. So it's a biological reaction, and you can see there's a lot of steps on it, but the key ones are the ones that are highlighted with yellow. These are the two monooxygenation reactions that are essential for getting the process started. And in the monooxygenation, oxygen, O2, is a direct reactant, as well as is an internal source of electrons that's shown as 2H. And so in the first highlighted step, we inserted a hydroxyl group, and in the second highlighted step, we insert another hydroxyl group, and we also break open the ring. And once we do this, now this molecule becomes easily accessible for all the normal metabolic reactions that all kinds of microorganisms can do. So we need to get past these first two steps. So we need the monooxygenase, we need the oxygen, and we need a source of the electrons, the internal electrons, the 2H. Okay, so back to the technical approach. So in our project, we studied several options for both stages, and here's what really, really worked well. For stage one, we used what we call the hydrogen-based membrane palladium film reactor. That's a catalytic, not a biological reactor. And in the second stage, we use the oxygen-based membrane biofilm reactor. That is a biological reactor. So let's start taking a look at what goes on inside these reactors. Okay, so let's start with the first stage, the palladium film reactor. So what we do is we produce palladium nanoparticles on the membranes. And as you can see here in this graphic, what palladium as a catalyst does is it absorbs hydrogen that we're delivering, and it actually absorbs it as activated hydrogen, single H's. It also absorbs the chlorinated solvent, in this case TCE, in an activated form. Now, on the surface of the palladium, these two activated forms come together, and they step by step do reductive dechlorination. You can see the chlorines coming off in the several reactions here. Now, what's really important here is that bottom reaction. Now we've got all the chlorines off already, and there's still one more step of reduction, and that is the formation of ethane, which is released. So with this palladium catalyst, we can go all the way to reducing the ethene to ethane. So that is really, really important to the success of this system. Okay, so that was our great theory. It seemed like a wonderful idea. So when we started the project, the first thing we did was test the basic theory. And so here is a graph of one of our sets of experiments, phasor batch experiments. We fabricated palladium nanoparticles. We put them in contact with TCA and TCE. TCE results are on the left, TCA results are on the right. In both cases, you can see within 60 minutes, we removed all of the original material, and we produced almost all ethane, including with TCE. So it was produced all the way to ethane. So it worked. It worked like we thought it should work. So that was reassuring. Similarly, for the second stage, the oxygen-based MBfR, we wanted to make sure that this ethane thing was really going to be successful. So we started up an MBfR, and we exposed, after we got a good biofilm, we exposed it to various potential substrates that would induce monooxygenases that might do the job. And so we had helium that's inert, that's the control. By the way, you can see there's a small decrease in dioxane because there was a bit of volatilization loss in our system. We had methane, nothing happened. We had a butane, nothing happened. We had a propane, we started to get some monooxygenase activity, but when we added ethane, we got by far the best monooxygenation activity. So this gave us reassurance that we really had the right material being formed, ethane, to really promote the second stage reaction. Okay, so armed with this confidence, we now went ahead and started to study the two stages in their various configurations. So we did TCA and TCE in the hydrogen-based MBfR, and we did it at the bench scale, and you can see it's our typical setup with two columns there. The key is that we form the palladium nanoparticles directly on the membranes right in the reactor. And so you add oxidized palladium salt, and you add hydrogen to the membranes, and after a little while, you start to reduce a few palladiums to elemental palladium, and they form nuclei, and then you get this autocatalytic reaction. It goes faster and faster and faster, and after a while, you get what we see on the right. You get this black coating of palladium nanoparticles on the fibers, and this coating is really stable. It's really, really stable. So it turns out this is actually quite simple and easy and very effective. So this is what we did. And then we ran experiments with these coated fibers. And here's one of our experiments. It's illustrative of what we always saw. So when you look at this graph, we have an experiment lasted about 36 days. Across the top, you'll see the dark black line showing that the influent concentrations of TCA and TCE were each 1,000 micromolar. We then ran them through the system here, some various conditions here. And the key thing is if you look at the end, you can see that if you look at the colored symbols at the bottom, they're almost zero. So we had almost 100% removal of TCA and TCE. And then we had small amounts of dichloroethane and monochloroethane in the effluent, but not very much. So we had 93% conversion of TCA and TCE to ethane. So that is really a huge success, and we're very, very, very happy about that. Okay, so in parallel with running these tests with the hydrogen-based MBfR, we also did dioxane in the oxygen-based MBfR. And so we did a lot of experiments. Here is one good illustrative experiment. So we inoculated the MBfR, and we started delivering ethane and dioxane, and you can see the ethane concentration was just under 2 micromolar, and the dioxane concentration was about a half a millimolar. And so those are, of course, the solid lines going across the top. So if you look at the circles, the little black circles, you'll see what happened to the ethane. It took some days for this to grow a really good, mature biofilm, but after 20 or 25 days, we had a very mature biofilm, and we were getting 100% oxidation of ethane. Once this happened and we had a good biofilm, you could see what happened to the dioxane. And by about 30, 35 days, it was all gone too. So we got greater than 99% removal of dioxane after we had grown a nice biofilm with the ethane. So another big success. Now, we did each part individually. The big test is we put them together. We create the synergistic two-stage system. So here's what we did. We literally just hooked up the two systems. The effluent of the hydrogen-based MBfR became the influent of the oxygen-based MBfR. So that's all we did. We just hooked them up. And we ran a lot of experiments with this. We ran about 130 days of experiments with all kinds of different loading conditions. And, so there was a lot of trying things out and learning as we went on. So I'm going to show you one result towards the end where we think we really got this lined up. And this is also indicative of a typical groundwater contamination scenario. So in this part of the study, we were feeding dioxane at about 0.2 micromolar and TCE and TCA each at about 0.1 these are millimolar, excuse me, I just spoke millimolar. So if you look at the solid circles, the filled circles, this is the effluent of the chlorinated solvents from the hydrogen-based MBfR. And you can see we were getting most of it out. Keep in mind that this is the sum of all chlorinated solvents. It was not TCE or TCA. They were gone, but it was a little bit of DCA and a little bit of MCA. So overall, we had about 90% removal of all chlorinated solvents. Now, what's more interesting are the open symbols. So first of all, looking at the open blue triangles, you can see the dioxane, the fate of dioxane. And we got some initial removal, but as the biofilm matured with these conditions, you can see the dioxane went down and down. And by the end, we were down to below the detection limit. So it looks like it's zero. It's below the detection limit. Now, it's also interesting with those open circles. Look at those open circles. These are the chlorinated solvents, a little bit of DCA, a little bit of MCA. And you can see as the biofilm in the second stage matured, they went down to almost zero as well. And we expected this. We expected that we could do aerobic degradation of DCA and MCA, and we did. And so we got everything removed in the two-stage process. So to wrap up with some overarching conclusions here, we created a two-stage system with the synergistic, removing TCA and TCA and TCE in the first stage, reducing them to ethane, using the ethane in the second stage then to biodegrade the dioxane here. And we got essentially complete removal of TCA and TCA in the first stage, and then the ethane from the first stage was effective for stimulating dioxane biodegradation in the second biological stage by being the molecule that induces the monooxygenase and also provides electron donor to grow the organisms and to drive the monooxygenase process. So it was truly a synergistic system. So we're continuing on this. We still have a continuing SERDP project. We're focusing on the second stage now. It's the newer one, so we're focusing in on that a lot, looking at 1,4-dioxane. We're particularly interested in how much ethane do we need to have going into the oxygen-based MBfR to make sure we get really good dioxane removal. So that's a big focus. And we have a modeling study as well as experimental studies being conducted by our team at ASU and also at Florida State University. Now, we think we're going to have great results here in this current stage, and we hope to be soon prepared to design and carry out a pilot test with the real water out in the real site. So we hope that that's going to go. And by the way, we also use this system for a number of other things of interest to the Department of Defense. We've been very successful at breaking down PFOA, RDX, and HMX with this same system here. So I'm not talking about that today, but it's very promising for other things too. So my last slide, benefits to DoD. Well, we have created a synergistic system. It allows us to have a single treatment system for TCE, TCA, and 1,4-dioxane. It's a simple system. The only inputs are hydrogen gas and oxygen gas, and they can be generated on site, say by electrolysis. It involves nothing hazardous, no hazardous chemicals, no hazardous conditions. Doesn't require a lot of energy to operate, so it's a safe, relatively low-cost system here. And it builds directly on existing technology, so we're not starting from scratch. We actually have a technology on which we can build as the foundation for that. So with this, I'm to the end, except acknowledging that there are a lot of people who work on this besides me, and here are all the names of the key researchers at ASU and Florida State. And with that, and also our collaborator at APT Water. And with that, I'll stop, and there's my contact information. So I'm ready for some questions if they're ready for me.
We have lots of questions for you, Bruce. So let's get started with one from the NRC. How stable is the palladium catalyst in your system? Does it undergo any poisoning or other deactivation mechanisms?
Yes, that's a really good question. So first of all, we of course have tested this extensively. So I showed you, I described the way in which we produce these nanoparticles directly on the membrane in the reactor, and then I showed you pictures. We have tested whether those particles are stable, and they are completely stable. We have almost zero loss over extended periods of running this reactor, and we've analyzed for it, and we find almost no palladium leaving the reactor. So that this autocatalytic process in the reactor creates really stable ones. The second question is, could they be deactivated by something? Because we all know that there are things that will deactivate catalysts. So in our work with the TCA and TCE and with Dioxane around, we found absolutely no evidence of any deactivation in this system. We operated the systems for many, many months. We never had to reactivate or clean or do anything. So for the system with the TCA, and Dioxane, the answer is no, we don't really have any evidence of any deactivation.
Thank you, Bruce. The second question is from the New Jersey Department of Environmental Protection. At what point can your two-stage system be realistically used to remove contaminants at the field scale? And are there potential applications for homeowner and large-scale water supply wells?
Yeah. Okay. So we feel that we will be ready to move this into a pilot test at the end of our project, which is this year. And we would love to be able to do that. Again, we are partnering with APT Water, which means that we have available pilot units that simply need to be adapted to this particular application. So we're able to do pilot testing relatively soon. Of course, you have to do the pilot testing. You have to deal with the realities of the field, and we haven't done that for this application yet. But it's not that long to the future. I see this as being something that can be done for, say, small water systems to large water systems. These systems are modular. You can upscale it simply by adding more modules, much like you do with, say, ultrafiltration. So they can go larger. I don't think you'd put one of these in someone's home, but I think you could do it from small water utilities on up.
Great, thank you. A related question to this, standard 1,4-dioxane ex-situ treatment systems can be quite energy intensive. Have you considered how energy intensive the system might be when operated at the full scale? Yes,
yeah, we have done that. We did, in fact, a fairly thorough techno-economic analysis of this as part of the first stage of our project. And it's not energy consuming. And then the main energy that's supplied is we have to pump the water through it. So that's the big energy cost of just pumping the water. And we have developed strategies to minimize the head loss and the pumping costs on it. You're producing a small amount of oxygen and hydrogen, and this is not a big energy consumer either. And we also are not using any extreme temperatures, so you don't have lots of energy costs to raise or lower temperatures.
Great, thank you. This is a question from EPA. Are you studying or considering modifying or optimizing the biofilm feature, or are you just going with whatever the microorganisms provide in the biofilm?
Yeah, that's a good question. So I often get asked variations of this question. The biofilm, it's what we call a volunteer activity. The organisms that want to be there because they're really good at it, in this case, oxidizing ethane and doing monooxygenations, they're going to be there. We're delivering oxygen, we're delivering ethane, delivering dioxane. So we're going to naturally select the very best microorganisms in the process. So we don't need to do any genetic modifications or anything like that. We will naturally select these. And these are not weird reactions. These are pretty normal everyday reactions. You just have to provide the right environment to make sure you actually select the best organisms. And that's what we provide.
Great, thank you. Another question from the New Jersey Department of Environmental Protection. When you oxidize the TCE and TCA to ethane, do you see any chlorinated byproducts, and do you anticipate any problems in effluent streams?
Yeah, okay, so first of all, we reduce them, we don't oxidize them. It's a reduction process. And, you know, as I showed in one of my early slides, it's a stepwise reduction on it. So when you're doing biological reductive dechlorination of TCE, there's always this big risk as you're going to, the process is going to stop at monochloride and you're going to have, you know, big problem. So we looked at this, you know, with our palladium based system, and because we were concerned, and what we found is there was absolutely no accumulation of any of those partially dechlorinated intermediates from TCE, the ones that are really dangerous. We did see a small amount of monochloroethane and dichloroethane coming out of the first stage, but it was then oxidized in the second stage. So it turns out none of them broke through.
Great, thank you. This is a question from one of the university partners, UNC Charlotte. Can the oxidative stage possibly be running under air instead of oxygen and still work for 1,4-dioxane?
That's a good question. The answer is probably yes. We haven't directly tried it, but we have run the oxygen-based MBfR with air in other settings, and it has worked. In this particular setting, though, it's really not so advantageous to do that when we're coupling these two processes, because the most likely way that we're going to produce hydrogen is by electrolysis. And when you do electrolysis, you produce hydrogen and you produce oxygen, and so you've already got the oxygen source naturally available. So, you know, in this particular setting, you know, there's not a big advantage of going with air.
Great, thank you. This question has to do with potentially adapting your technology. Do you think that the synergistic system can be adapted, for example, for in situ treatment?
That's a good question. Of course, we're testing it now for ex situ, directly for ex situ treatment. But so could it be done in situ? And I think the answer is yes, if you're using what we'll call the permeable reactive barrier approach, in which you could then, you know, you channel the water flow through the permeable reactive barrier, and then you could put in the delivery of hydrogen and the delivery of oxygen in there under controlled conditions. But I don't see it just doing it, you know, without something like the permeable reactive barrier.
Thank you, Bruce. Can the system work if 1,4-dioxane is the only contaminant, if you don't have any chlorinated solvents?
Yeah, that's a good question too. So yes, in fact, in our first stage of our first set of experiments, we did run it this way. We just put in dioxane, and we delivered ethane to the, you know, to the organism. So in the case where you only had dioxane, you would have to also add ethane, which you could either add to the influent water, or you could actually put another set of membranes in to deliver ethane gas. Well, we haven't tried that approach yet because we haven't needed to with the synergism that we have, but it could easily be done.
Great, thank you. Here's another question from the New Jersey Department of Environmental Protection. Have you considered iron as a potential problem with the biofilm and the catalyst? Okay,
that's a pretty good question here. So what could be a problem with iron? If you had a high iron concentration, it probably would be ferrous iron. I don't think that would have any impact in the first stage. The second stage, it might create a problem if you started oxidizing the iron and you started precipitating iron oxides in the biofilm, and it could cause some operating challenges. That's the kind of thing you look at when you're doing at a pilot in case there is iron in the water. This can be managed. We have what we call biofilm management protocols to clear out excess biomass. In this case, would also be with excess, say, ferric oxides. So there are ways to do it, but you need to be aware of it and take it into account in the operation.
Thank you. We have a lot more questions than we can cover in this Q&A session, so we'll save some of them for the final Q&A session.
Okay.
But one last question for you. One last question before we let you go and transition to Jens. This is from Arizona State University. In the palladium hydrogen membrane film reactor, how was it determined? How did you determine the amount of palladium that was needed to dechlorinate TCE and TCA?
Yeah. Yes. Well, all right. So that's a good question, and we haven't studied it as systematically as we would like down the road on it. I mean, we have a standard protocol for preparing the nanoparticle film. A certain amount of palladium we add and for a certain amount of time, and basically we reduce and precipitate all the palladium. There's nothing left in solution. As you saw from the picture, it creates a black. It blackens the thing. So it's multi-layer film. So we know that's enough. So we would like to more systematically study, could we use half as much, or would it work better if we had twice as much? We haven't had time to systematically look at that, but we've got a very good protocol, and we can easily put on more or put on less by just putting less or more palladium in the solution where we form the film.
Thank you so much, Bruce, for a phenomenal presentation and a great Q&A session. We'll get back to you in the final Q&A session, but it is now time to introduce our second speaker today, who is Dr. Jens Lottefogel. Jens is a research assistant professor in the Department of Civil and Environmental Engineering at Colorado State University, and also co-director of the Center for Contaminant Hydrology at CSU. Jens's research focuses on the environmental fate of emerging contaminants and specifically their degradation in natural and engineered systems. He has developed sustainable water treatment technologies, theoretical models for contaminant degradation prediction, and various advanced analytical methods with a focus on high-resolution, accurate mass spectrometry. Besides 1,4-dioxane and chlorinated solvents, Jens is currently working on solutions for managing PFAS, nitroaromatic compounds, perchlorate, and oil and gas produced water. Jens, we're really happy to have you with us. Please proceed.
Thank you, Rula. I'm happy to be here. Thanks for the invite and giving me the opportunity to talk about our research on bioelectrochemical treatment. We've been doing that for a couple of years and for a couple of contaminants. But of course, today I'll talk about 1,4-dioxane and chlorinated solvents. So on the agenda for today, we have, I'm going to start with a problem statement followed by a technology description. I'm going to then mostly focus on bench scale performance of the technology as developed under SERDP. And then because we don't want our efforts to stop at the bench scale, I'm going to show a path towards scale up 2 and the efforts that we're undertaking there currently. And then finally, I will end by talking about the conclusions and the benefits to the Department of Defense. So 1,4-dioxane is a recalcitrant organic compound, but it is biodegradable. Now, the monooxygenases that are involved in the biodegradation need molecular oxygen, and so this happens under aerobic conditions. And it can happen either co-metabolically by a whole range of organisms. This is a rather fortuitous reaction, so the organisms don't really have an advantage in doing this, but the enzymes are just present. And it can also happen metabolically, most notably by a bacterium that's called Pseudonocardia dioxanivorans, CV1190. I'm just going to refer to this as CV1190 from here on, but this is the organism that we tested in developing the technology. And CV1190 is a microaerophilic bacterium that doesn't really need much oxygen. It can, of course, if it's present. It also survives anoxic periods and pretty high solvent concentrations of solvent stress. And it generally has a pH optimum somewhere between 5 and 8 for growth. Now, if biodegradation works for you, that's great. It's typically more efficient and better than we can engineer something. But often it is a problem for several reasons. First of all, if you are looking at co-metabolic processes, especially, you do need an organic co-substrate. So in biosparging, for instance, propane can be injected, but it is something that you need to take care of. Secondly, the MCLs, the maximum contaminant levels in various states, as Dr. Rittman just showed, are at ppb to sub-ppb concentrations down to 250 ppt. And those concentrations are challenging to meet by microorganisms, especially metabolic ones that really don't get much energy out of degrading this in the first place. And then finally, 1,4-dioxane is used as a solvent stabilizer, so it often co-occurs with chlorinated solvents. And these chlorinated solvents inhibit biodegradation. What I'm showing here is a figure from previous research by my collaborator, Shaylee Mahendra at UCLA. And what she showed, or her student showed, is that these chlorinated solvents inhibit 1,4-dioxane biodegradation to different levels. TCA not so much, but there are others that do this really strongly. And from what we know at this point, at least, 1,1-DCE, dichloroethene, is the chlorinated solvent that inhibits aerobic biodegradation of 1,4-dioxane the most. So what I'm showing here then is a schematic of an electrolytic cell where we have an external DC power source that applies current to an anode and a cathode, or multiple anodes and cathode. And the anode is the positive electrode, the electrode where oxidation is occurring. So this is where we can turn reduced organic carbons, such as 1,4-dioxane, to CO2. And the cathode is then the negative electrode where reduction is happening. So we can do something like reductive dechlorination and also other reactions. But the thing is that we're doing this in water, of course, and water is a great redox buffer, and it can be oxidized and reduced itself. And so a lot of the electrons that we're providing, or really most of the electrons, go into the anodic oxidation of water to oxygen and into the cathodic reduction of protons to hydrogen. So in a way, it is a wasteful process if we're just doing this electrochemically, and thus arise the idea of using these gases to stimulate biodegradation processes. We have studied these processes with different dimensionally stable electrodes or anodes over time. So these are non-sacrificial electrodes that are stable over long periods. And you can see a couple of materials here that we've tested. The results that I'm presenting today mostly focus on a titanium anode that is coated with a tin or a doped tin oxide substrate. And then what you can see too here is a close-up of the electrodes that we're using. So we're not using sheet, stick, or plate electrodes. We're actually using mesh electrodes with small openings. And the reason for that is that we can use these to build permeable reactive barriers if passive in situ treatment is something that you're interested in. So on this slide, you see photographs from a project at the Pueblo Chemical Depot, where my co-PI Tom Sale on this project showed in one of his 2 ESTCP projects that these mesh electrodes can be mounted on vinyl sheet or sheet pile wall, basically. So there are openings that are cut into these interlocking sheet pile wall panels, and the mesh can be mounted on it. And then you can sink that basically into a trench and backfill it and install monitoring devices, for instance, and just wait for the contaminated water to pass through. And you can run that very sustainably by solar power, for instance. This was a project in Colorado where we do have a lot of sun. And if you're worried about too much above ground infrastructure, then you can eliminate that too and just use power from the wall, but you can run this with solar power. So this brings us to our hypotheses. And obviously, we have in the bottom left the direct anodic oxidation of 1,4-dioxane in such a system. But again, because this would be wasteful and we're generating all these gases, the idea was to use the oxygen as an electron acceptor for aerobic 1,4-dioxane biodegradation processes. We also hypothesized that the 1,4-dioxane is being broken up, not necessarily completely mineralized, into intermediates, oxidation intermediates, that can serve as growth supporting intermediates because the energy return for the microorganisms would be much better than using 1,4-dioxane directly. And then finally, because 1,4-dioxane co-occurs with chlorinated volatile organic carbon compounds at a lot of sites, we also thought about the benefit of electrochemical removal of inhibiting co-contaminants. So what you see here in the top is a schematic of our first generation reactor. These were lab scale, 4-inch clear PVC, 4-inch inner diameter clear PVC columns that were equipped with several ports, sampling ports for liquids and for solids. And in the beginning, we really only had one electrode pair in there, a mesh electrode pair, so that the water could flow through the column and test what happens when we inoculate these columns with CD1190. So the CD1190 culture was grown on sand first and in the presence of 1,4-dioxane until it reached steady state. And then the columns were filled with this inoculated sand. And then we would flow water through at flow velocities somewhat typical of groundwater and porous media, somewhere around 1 to 1.5 feet per day. And in the graph below here, you see the CD1190 cell abundance. This was the CD1190 abundance was measured as abundance of the dioxane monooxygenase functional gene. And what we saw here is basically that along the column, about 10 centimeters down gradient of these electrodes, we had a maximum, which indicated that this would be a sweet spot for the bacterial abundance. And we used this information to then later design a second generation bioelectrochemical reactor. We also tested the electrochemical oxidation of 1,4-dioxane. As I said, it doesn't necessarily get mineralized completely. So at the groundwater flow velocities we had used here with this one electrode pair, we got somewhere around 50% complete mineralization, but we also formed a lot of intermediates. And we applied NMR, high-resolution mass spectrometry, ion chromatography, several techniques to identify those. And you can see them here. Diethylene glycol is actually a hydrolysis product, which happens at the very acidic surface of the anodes. So 1,4-dioxane can undergo hydrolysis, but you need very low pH values. And all the other intermediates that you're seeing here are true oxidation intermediates that are certainly much more readily biodegradable than parent compound. So as I said, we used the information from the qPCR analyses to design a second generation reactor. I'm not showing a schematic here of this reactor because it just looked like the first generation reactor. It was a 4-inch inner diameter clear PVC reactor. But in this case, the reactor held 3 electrode pairs, mesh electrode pairs, spaced 15 centimeters apart. And you see that indicated here in these plots as vertical dashed lines. And what you can then see in the top left corner is the dissolved oxygen as a function of the distance through the column reactor. And what you see then too is that past the electrodes, oxygen got enriched. So we got DO concentrations at both the applied voltages of 3 volts and 6 volts. And those are cell voltages, I should mention. And at 3 volts, we didn't really see much of bubble generation. At 6 volts, the bubbles were clearly visible, but the DO concentrations weren't necessarily higher. So that tells us that the concentration of dissolved oxygen is really a function of the dissolution kinetics of the gas bubbles that we're generating. So in an in situ installation deep down in the aquifer, we would expect that we can run this more efficiently. So there is a scale effect. We also looked at the pH range, of course. That's what you see on the bottom right. And what I try to indicate here with this orange field is the optimum pH range for CV1190. And then you see that under all conditions applied, 0 volts, that would be our control, and 3 and 6 volts applied, that the bulk pH stayed circumneutral and conducive to biological growth. So let's look at what's happening to 1,4-dioxane in these reactors. We had an influent concentration to these reactors of right around 100,000 micrograms per liter. So that's 100 milligrams per liter, and that's quite a bit higher than you would find at most field sites. But these cases actually do exist, for instance, in wastewater, and we even had a pilot scale study going at a site with over 1 million micrograms per liter of 1,4-dioxane, or 1 gram per liter. So, and there is really no harm in starting high. It shows the limits of this technology, and if you have lower concentrations, then certainly these results are still relevant to you. So what you see here in this plot then is the normalized 1,4-dioxane concentration for several test cases as a function of distance through the reactor. Again, our electrodes are indicated here as vertical dashed lines. And at 0 volts, in the absence of an applied power and in suboxic environments, there was no degradation of 1,4-dioxane by CV1190. With 3 volts applied electrochemically only, there was a little bit of removal, but that really changed when the columns were bioaugmented. You see the pink curve here with the solid markers, that the concentration goes down, and we're looking at about 60% removal of 1,4-dioxane, so about 60,000 micrograms per liter. And then at 6 volts applied, you see electro only. Those would be the blue dashed lines with the open markers. We do get quite a bit of electrochemical removal, but again, we bioaugment the reactors, and then the solid blue lines show that the removal was very rapid, basically only after 1 electrode pair. Most of the 100,000 micrograms per liter were gone, and at the end of the column, we were below our detection limit of 3 micrograms per liter. So that's a removal of more than 4 orders of magnitude. Next, we're looking at the normalized concentration of 1,1-DCE as a function of distance through the reactor. We chose 1,1-DCE as a model chlorinated solvent here, again, because we do like challenges, and 1,1-DCE is the strongest known inhibitor of 1,4-dioxane biodegradation. And you can see that in the control experiment at 0 volts, we do have some losses of 1,1-DCE, but it remains in the column at pretty high concentration. So the influent concentration was 5 milligrams per liter. At 3 volt in the bioelectrochemical reactor, we do see a significant drop of 1,1-DCE to about 97% at the end of the column, but with quite notable concentrations around 1 milligram per liter persisting through the electrochemical or electrochemically active part of the reactor. And then we can see that at 6 volts, 1,1-DCE is very rapidly applied, basically by 2 orders of magnitude. So somewhere to the range of very few micrograms per liter. So of course, we want to find out what that does with our process. And what we're looking at here are all the bioaugmented columns. So this is only bioelectrochemical treatment. And we are comparing here bioelectrochemical treatment in the absence of 1,1-DCE, in the open markers, and in the presence of 1,1-DCE with the closed markers. And again, in the control 0 volts, not much happening with 1,4-dioxane. at 3 volts electrochemically or bioelectrochemically in the absence of 1,1-DCE. Those are the open squares. We get about 50% removal. And in the presence of 1,1-DCE, we do have a significant inhibition. So that's the difference between the two magenta colored lines here. So even though DCE was removed by about 80 to 90%, we still get a lot of inhibition here from 1,1-DCE. At 6 volts, we can see that in the absence of 1,1-DCE, again, rapid degradation, and in the presence of 1,1-DCE, even though we are removing 2 orders of magnitude to low micrograms per liter, we see quite a bit of inhibition in the first part, in the electrochemically active part. So it takes longer, even if there's just a little bit of DCE present, for the microorganisms to help with the process. We also track the fate of chlorine or chloride. Both chlorine was present as 1,1-DCE. Chloride was present in the simulated groundwater that we had used. An electrochemical treatment is an advanced oxidation process, and all advanced oxidation processes oxidize chloride too, unfortunately, to form oxidation byproducts such as chlorate and perchlorate, and that's what I'm showing here. And probably as expected, at higher applied potentials, you form more chlorate. And we also found perchlorate at concentrations up to 70 micrograms per liter. At a lower voltage, 3 volts, there was no perchlorate, but there was still some chlorate that we found. So lower voltage has the advantage of less oxidation byproducts. But even at 3 volts, which is really the minimum where we saw any reaction, you are still forming these oxidation byproducts. So to look at the cost of this process, the major capital cost driver are the electrodes, and really mostly the anodes. You can use cheap cathodes for the process. And this is quantified by the ASAO, or the anode surface area per order of magnitude of contaminant removed. So in this case, 1,4-dioxane. You see that on the y-axis here plotted, and the differences are quite dramatic. First of all, in terms of electrode cost, it is much more efficient to run higher potentials because you need less electrodes for the conversion. And then you can also see that by augmenting the reactor with CV1190 and doing bioelectrochemical oxidation, you are lowering the capital cost by about an order of magnitude. Major operational cost here, and this is quantified as an EEO, or the electric energy per order of magnitude of contaminant removed. And again, under electrochemical conditions, you can see that actually at 6 volts, we use less energy per 1,4-dioxane unit removed, and that's just because it's much more efficient or effective for 1,4-dioxane oxidation. The bioelectrochemical oxidation, it reverses a little bit. The lower potential seems to consume a little less energy, but the difference is not very strong. But again, when you compare electrochemical with augmented bioelectrochemical oxidation, we're lowering the operational cost again by about an order of magnitude. So on this slide, we can basically see where we're at. This is the famous technology triangle from Pankow and Cherry, and we are with this technology at the pilot scale now. As I said initially, we don't want to just end our efforts at the bench scale, but we want to drive this really to application. Now, the pilot scale is the scale basically where we as academics team up with consultants, and we've done that here with Jacobs to take this technology to the next stage. And so together with Jacobs, we designed a pilot scale system, which we are terming Electrobiogeochemical Reactor, or EBGR, which is at this point an above ground treatment. And we are trying this at the drum scale at a site that is contaminated with 1,4-dioxane and mixed CVOCs. And you can see that the water comes here into an equalization tank and then goes to bioelectrochemical oxidation. So this is where the electrodes sit, and we had done initial tests with the groundwater at different potentials to find the optimum current. And for this specific site groundwater, we settled on 8 volts. And then this reactor is backfilled just with gravel, basically, to help the gases escape. So what's not shown here is the gas management, but you do have to help the oxygen and the hydrogen to get out, or in the case of oxygen, also to become dissolved. And then from bioelectrochemical oxidation, water goes into an anaerobic biogeochemical degradation reactor that has certain proprietary amendments to it to support microbial processes. And in this stage, we're basically trying to get rid of any residual CVOCs that may not have been oxidized in the first step. And we're also trying to get rid of any potential oxidation byproducts, such as chlorate or perchlorate, that we may form in the first reactor. So this concept is really based on Jacob's concept of the subgrade biogeochemical reactor. This would be another potential full-scale application if a permeable reactive barrier is not of interest. We can also run this as an ex situ treatment in above ground reactors, but in general, people like in situ treatment. So in this case, this EBGR is basically a recirculation cell that is backfilled with proprietary amendments again. And then the groundwater is pumped, the contaminated groundwater re-infiltrated into the EBGR, and that's where the electrodes would sit and do their magic. And from there, the water goes back into the groundwater, hopefully cleaned. So with that, I come to my conclusions. First of all, what we've shown is that we can lower 1,4-dioxane concentrations to low or possibly even sub-ppb concentrations, even in the presence of the most inhibiting CVOCs. And even if we go from starting concentrations as high as 100 milligrams per liter. We can also conclude that this technology works by truly synergistic or over-additive treatment effects, and those are the microbial utilization of the generated O2 from the anodes, transformation of persistent contaminants into growth-supporting intermediates, and then also the removal of inhibiting co-contaminants. And with that, we can run the system at significantly reduced O&M costs compared to electrochemical treatment alone. And then also, if we do bioelectrochemical treatment and we can maybe work at lower potentials, then we would also decrease byproduct formation. So the benefits to the DoD here is that, first of all, we have a new technology in the toolbox to destroy 1,4-dioxane to the very strict, and also a technology that is effective where CVOCs co-occur, and that's certainly often the case. This installation can be implemented ex situ as above ground reactors, and we have pilot tested that too, or it can be installed in situ, for instance, as a permeable reactive barrier or as an EBGR. It is also a highly adjustable system. You can run this active with pumping or hopefully passive in a PRV. What we haven't tested yet is whether the technology is effective with other microorganisms, but we do suspect that that is the case. So these could be, for instance, co-metabolic 1,4-dioxane degraders, or maybe even organisms that come from the very site that have seen 1,4-dioxane already, maybe even without bioaugmentation, but bioaugmentation certainly helps. And maybe even bioaugmentation with reductive dechlorinators to help on the reductive side, because we still need to find a use for the hydrogen gas that we're generating. And then finally, we also believe that this works for other persistent contaminants and mixtures. We have proven that for a couple of contaminants, some nitroaromatic compounds, and then currently within the same SERDP project, we're working on extending this technology for PFAS. So with that, I'd like to acknowledge my project team here, Shaylee Mahendra at UCLA, Tom Sale at CSU, those are my two co-PIs. Then Nassim Pika, who was my former postdoc, who did most of the lab work that I showed here today and who's now with CDM Smith. And then finally, Jeff Gamlin at Jacobs, who we collaborated with to design the EBGR, excuse me. And with that, I would be happy to answer any questions. And if time is not sufficient, then you have my speaker contact information here. Thank you.
Thank you so much, Jens. We do have plenty of time for questions, so let's go ahead and get started with a question from the NRC. At many sites, dioxane and CVOCs are addressed with advanced oxidation technologies such as activated persulfate. How is your technology advantageous to other demonstrated technologies?
Yeah, so it depends what you compare it to. First of all, it is another tool in the toolbox, and this is no silver bullet that is your best approach at every site. So if you compare it to persulfate, for instance, persulfate is certainly effective, but you do depend on the distribution of the injected substrate, and then also you are basically doing ISCO alone, only chemical oxidation. I think one of the main themes of my research is to look at treatment trains and try to combine chemical oxidation with biological oxidation processes, because in general, when biology works, it outcompetes our engineering efforts. And so in certain cases, maybe also driven by the lithology of the subsurface, it may be beneficial to, say, put in a trench and homogenize groundwater flow and think about something like a reactive barrier. So yeah, again, not a silver bullet technology, but certainly something you may want to consider depending on the specific site.
Thank you, Jens. This is a question from Atom. What is CB1190 gaining from the electrochemical system? Is the electrochemical system a source of oxygen for the microorganism?
Yes, that is the main advantage for CB1190. So CB1190 can metabolize 1,4-dioxane. It can live on 1,4-dioxane as the sole carbon and energy donor. So it doesn't really need the intermediates, although it does benefit from the intermediates because it is more efficient to live on the oxidation intermediates. But we do believe that the critical part here is really the oxygen. Without the oxygen, the CB1190 will not do any 1,4-dioxane degradation, basically as shown in the control experiments where we did not use an applied voltage.
Great, thank you. Can you tell us what the cost of the electrodes is and how long they last before you have to replace them?
Yes, so there are quite vast differences. Among the materials that I've showed, we work a lot with iridium tantalum mixed metal oxide electrodes, and all of them are available as mesh electrodes. These specific ones that I just mentioned, they are used in cathodic protection of instance, and so they are widely commercially available, and we pay around $40 per square foot. That's about the low end at the moment, I would say. If you need something like, if you're looking at something like boron doped diamond, that may be overkill for 1,4-dioxane, but it is considered for something like PFAS. You're looking at, well, more than 2 orders of magnitude above that. The electrodes that I showed here and that we used in our SERDP project, those are tin oxide doped electrodes. They are at the moment commercially available from Evoqua, I believe. These are more expensive, at least at the quantities that we have purchased them by a factor of up to 10, I would say. But the thing is that these electrodes are much more efficient than anything else that we've tested for titanium for 1,4-dioxane. And we do believe, because tin is so cheap, that if these materials become widely used, that they could become cost competitive with the cheapest electrode material that's available currently. And of course, that brings me to the second part of your question, what's the longevity? These tantalum, iridium tantalum oxide electrodes, they have been tested by Tom Sale in 2 PRB installations. At least one of them went up and beyond 2 years. And if you take good care of them, which means frequent polarity reversal to get rid of scale, then these materials should last for at least months, if not years. For these novel doped tin oxide electrodes, we've done accelerated lifetime tests, and they should have about the same service life as the ones we've tested before. So again, months to possibly years, depending on water quality.
Great, thank you. And related to this, do you expect certain water quality parameters to impact either the electrodes or the electrochemical process in general?
Yes, the water quality plays an important role, and that's something you want to investigate beforehand. So, for instance, this could be caused by both high organic and inorganic loads. So on the organic side, I had mentioned this one site where we treated 1,4-dioxane at over a gram per liter. And what happened at that site is that the electrodes became poisoned. So some of the intermediates, they covalently bonded to the surface of the anodes and reduced the lifetime of the electrodes to a couple of months, 4 to 6 months or so. That may be a unique case. We haven't seen that anywhere else, but the inorganics are something you always want to think about, especially precipitable species. So Dr. Whitman had addressed iron previously. Iron can always be a problem if present at high concentration because you may form sludge in reactors. And then you would need some means of sludge removal. The iron can also precipitate on the cathode, and so can carbonate scale. So the cathode is the bigger concern when it comes to, the anode is of concern when it comes to iron oxidation. The cathode is of concern when it comes to carbonate precipitation because you have high pH values. And again, what has been done at these sites where we tested that at the pilot scale, we have reversed the polarity, and by that we can manage and extend the service life of the electrodes.
Great. And one last quick question for you before we pull Bruce back into the discussion. For the process that you described, do you think the amount of voltage depends on the size of the study area? So if you were to go out in the field, do you think a voltage greater than 3 or 6 volts would actually be more effective?
Yeah, so the very low voltage, 3 volts, is basically just above the oxidation evolution potential of the electrodes. So again, as I said, these were cell voltages. The actual anode potential is somewhere around 2 volts under these conditions. And in a way, it is under these settings a setup that would compete with something like biosparging. So you're not getting the additional beneficial effects when you run this at higher potentials. And if we look at cost too, then to us it appears like the higher potentials are better. Now, it doesn't mean in general that the more power you apply, the more degradation you get. There is a potential at which the performance really levels off, or current, I should say, and where this whole process really becomes driven by mass transfer limitations. And that is basically the goal of preliminary investigations for each and every site. Before I start building anything, I would want to have a groundwater sample and determine what the best current and the optimum voltage is, and then use that specific voltage at the site. And with that, then I can also scale up or run scale-up calculations on how much electrode surface I need and how much power input.
Great, thank you, Jens. We're going to try and wrap up with some general questions for both you and Bruce. So let's get started with Bruce and the following question. In both the studies that you, Bruce, and Jens described, a 1,4-dioxane concentration several orders of magnitude higher than typical concentrations in groundwater were used. How do you believe your system will perform at more environmentally prevalent concentrations of 1,4-dioxane in the 10 to 100 ppb range? Bruce?
Yeah. Okay, I got it. So yeah, that's a good question. And that's actually one of the things we're testing in our ongoing phase of the project here on it. We're in the middle of it. Now, the thing to keep in mind here is that the organism depending on dioxane to grow. So as we lower the concentration of it, as long as we've got enough ethane around and enough biomass, then we should be able to get really, really good removals of dioxane from that. And so, like I say, we're in the middle of the testing, and I don't have all the final, the final answers, on this. But in general, that's what we are seeing. Is it's, because it's not depending solely on dioxane, we can drive the dioxane concentration very low from, low starting concentration.
Great, thank you, Bruce. Jens, would you like to add anything to Bruce's response?
No, not really.
Great, thank you. Here's the second question to you both, and we'll start with you, Jens. Are there other promising treatment train approaches for mix 1,4-dioxane and chlorinated solvent plumes?
Yes, I believe so. And as I said, as water technologies mature, we do believe that treatment trains are often more energy efficient if there are synergies that can be harnessed, such as in the two examples that we saw today. So another example that comes to mind would be a bio-augmented GAC, for instance. That's research that's just emerging out of my collaborator's lab, at UCLA, where sorption to GAC, or granular activated carbon, initially didn't seem like a good idea. 1,4-dioxane doesn't sorb very well to activated carbon, and it desorbs very easily once concentrations go down. So if you bio-augment GAC, for instance, with CB1190 and you have active degradation, then you can make sure the 1,4-dioxane becomes degraded. You increase the adsorption capacity and you decrease the risk for desorption. So I do believe there are a lot of other potential combinations that should be considered.
Thank you, Jens. Bruce, would you like to add anything?
Yeah, I'll add a few comments here. So the first thing I'll add is I really think that the strategy we use, where we're first reducing and then oxidizing, is the way to go, because it eliminates a lot of the problems that Jens identified in his talk with inhibition and things like that. So I think that's really good. Now, in our first stage of our project, we tried several approaches for the reduction stage and also for the aerobic oxidation stage. And the ones that I showed you today are the ones that by far work the best. So we think we've already kind of pre-selected down to really the best ways of taking this synergistic aerobic approach.
Thank you, Bruce. And one last question for both of you before we wrap up here. Bruce, you specifically mentioned other contaminants that your proposed process could potentially address, things like PFOA, RDX, and HMX. Mm-hmm. Are there other contaminants, for example, like NDMA, that your approach could be applied to?
Well, so when I'm talking about our approach, I'm talking about this two-stage system where you first do the reduction reaction and then you clean it up with the aerobic biodegradation reaction. And so we're looking for things that need a first stage that's reductive. And so you have anything that's fluorinated, well, this is something you can do reductive defluorination. Things that have nitrogen in it, like nitro species or nitro in the rings, these are really good candidates for being reduced. So anything that you want to reduce is a really great candidate. So it's things with halogens and things with nitrogen for sure.
That's a great clarification. Thank you so much, Bruce. What about you, Jens? Are you considering your proposed approach for other contaminants that are prevalent at DoD sites?
Yes, we are. So we're also looking at pure electrochemical treatment. And I think one of my slides actually said electrochemical oxidation can virtually degrade any organic contaminant. And to my knowledge, there is no organic contaminant that has been shown to be stable in these systems. It's really just a matter of the electrode material that you choose and the power you put into the system. But there are several reports now through several SERDP projects that even PFOS, PFOA, and other perfluorinated compounds can be completely mineralized. And I mean, those are, I guess, the most persistent ones that we know of. Now, whether the question is really, how do you do it most efficiently? Because electrochemical oxidation is not necessarily the cheapest process. So typically we only apply it to refractory organics. But yeah, we're using it on PFAS ourselves, again, in this very same SERDP project. For 1,4-dioxane, we've worked with chloronitrobenzenes and other compounds. All of these you can mineralize. Often you can make the mineralization process or the treatment process more efficient by coupling it to other technologies such as biodegradation or nanofiltration. So in terms of concentrate and destroy treatment trains. And on the inorganic side, of course, we can degrade them, but there are ways how to immobilize and precipitate metals, for instance, in mine tailings and other settings. So this can be addressed.
Well, thank you very much to both of you. I think we're all leaving this webinar with a very key takeaway message, which is the importance of treatment train approaches for addressing complex contaminants at DoD sites, and certainly SERDP and ESTCP have made a lot of investments in these treatment train approaches. So thank you both. And we're going to go ahead and wrap up. But before we do, I'd like to remind you that our next webinar on Thursday, July 9, is in the Insulation Energy Program area and focuses on securing DoD control systems and infrastructure from cyber threats. This webinar will feature Dr. Jonathan Butts and Mr. Billy Rios from QED Secure Solutions, and they will discuss a new baseline automated security enumeration and configuration tool to rapidly identify vulnerable, misconfigured building automated systems associated with DoD building and energy infrastructure. The webinar will also feature Mr. Colin Dunn from FEND Incorporated, who'll talk about low-cost data diodes for facility equipment monitoring to meet the needs of critical infrastructure managers across DoD. Registration is open, so please visit the SERDP ESTCP webinar webpage to register for this and other future webinars through the end of this calendar year. And before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your time.